Good morning, welcome. We'll be discussing chapter 20 from our data structure class. Chapter 20 is about graphs. So there'll be a few new terms in this chapter, and some of the concepts are kind of interrelated to unordered linked lists, and some of the concepts are new, especially how we actually structure our data, save our data, and traverse our data. So some of the terms we will be using are vertex, edge. There are a couple of graph traversal methods are discussed in this chapter, in chapter 20, especially depth first and breadth first. I'm going to demonstrate the depth first in our demo file, which is available on our LMS. And for your homework, you will be working on breadth first traversal method. So they're kind of similar, but how you access and traverse the data is slightly different. Some of the ADTs, abstract data type files, we are going to use from the previous discussion, so it's not new, especially when it comes to unordered linked list. It's the same linked list we are going to use, but application into graphs will be slightly different. So we'll discuss that once we get there. There are two types of graphs discussed, directed and indirected versus indirected graph. So I'll be highlighting both of those. And also, when you have a graph, you can actually have a weight on each graph, and I'll talk about the weight of the edge. So this is the edge. So this will be your vertex. So this is called a vertex, and this one is called the edge. And you can assign a weight for each one of those edges, and weight could be in dollars, weight could be in miles, weight could be in a specific value based on what kind of graph you are creating. And also we'll talk about minimal spanning tree, especially when it comes to evaluating and calculating those values based on the edges, the weight of the edge, and how you determine which is the most efficient graph in that case. So the data I'm going to use, this is the depth first data, and I'll show you how this is actually converted into graph format or tree format. Also, before we start, I would like to highlight a couple of things. That our goal is to finish chapter 20, so we can start the last assignment, assignment number 7. That will be our last assignment for this class, which will be due by hopefully by next Sunday, which is December 3rd. Next Monday, we'll be taking our final exam for our on-campus class. For online class, it will be a different schedule. For on-campus class, when you come back on Monday, based on chapters 20 and 21, we'll be taking this exam. We already have covered chapter 21 last week, so this will be our last discussion. This will be end of the book. So this is it. So after today, there'll be no more recording. I don't need to record you during the exam, so you're okay. So when you come in, we'll just take the exam. That will be our last activity. So you guys okay? Okay, shall we start? All right, I will not be able to show you this tree or this graph once I have the projector on, but we have the same image available in other places. So I'm going to go through some of the concepts first. Then I'll show you the graph, and I'll show you how we can actually traverse this graph, especially in the depth first format, and how the breadth first format uses slightly different way to traverse the graph. And some of the terms will be available from our PowerPoint. So if you have the PowerPoint, you can see those terms. You can see the definitions. If you have the book open, you can also see these definitions in the book. But I'll be highlighting some of the key areas. All right, I think we can go ahead and get started. So this chapter, we will be discussing some of the terminology of the graph theory, how it started, how to implement into ADT, and so on and so forth. So your chapter actually begins with this concept here. It's called Waynesburg Bridge problem. There was a river, and assuming this is a real problem, this is a real river, and what if you have there's an island, an island divides, there are two branches around the island, assuming this is a river, So this is some kind of river. There's an island here, and you can see the water is flowing from each side of the island. Now, the problem was, which was discussed theoretically, mathematically many years ago, that is it possible if you have a bridge or a bunch of bridges, you cross each bridge once and you can still reach to the starting position. So you go and visit each one of those bridges and you can reach or you can come back to the starting position. So this starting at one land area, can you cross all bridges exactly once and return to the starting point? So this was the problem. So in 1700s, the mathematicians and people who were into this kind of theory, they wanted to explore that is it mathematically possible that you can reach your starting point by crossing each bridge once. So Euler represented the problem as a graph and answered the question that it's mathematically not possible. So assuming you have, this is the starting point, you can start from any point. So if you go to point D, we call them vertex. So this is C is a vertex. So if you go to D, from D you go to A, and if you from A you go to B, and from B to D, remember you cannot cross this again. So you will not be able to get back to point C. So you try different options. It's hard to cross each bridge once and get to the same starting point. So this was the issue, and this actually created a new graph theory. So if you take math classes, especially advanced math, you will actually take a specialized area called graph theory. So you spend a lot of time discussing graph theory. There are some terms about sets and unions and intersections. I'm not going to spend time discussing those. Those are simple concepts that if you have some data in A and data in B, what is the union? What is the intersection? So those are simple concepts from introductory math. So over the past 200 years, graph theory has been applied to a variety of problems. What do you think? Where can we apply the graph theory problem? In what kind of industry they actually use graph theory? Any ideas?
Engineering.
Okay, so give me an example. Let's talk about electrical engineering, for example.
Okay.
So let's talk about grid. So where this can be applied. When you're building a grid, right now it's happening in Puerto Rico, they are trying to figure it out what is the most efficient way to build that grid, because the entire grid was already kind of obsolete. It was in bad shape. After the hurricane, it just collapsed completely. So graph theory is a perfect implementation in that case, because they can figure it out the most efficient way to build that grid. How about airline industry? Over the weekend, Thanksgiving weekend, we had 13,000 planes in air during the Thanksgiving one day, per day, during that time. 13,000 planes at one time. So the most efficient way to figure it out, the route for each one of those planes from point A to point B, and the graph theory will be most appropriate one to figure it out, which is will generate most revenues, most profitable for the airline industry. Same thing for the trucking companies. We actually have Cyber Monday today, which means Amazon and many of the other major companies, UPS and FedEx, they are evaluating the best route for their trucks. So graph theory will be best applied in that case as well. And you'll see some of the practical examples you'll see in the book as well. So model electrical circuits, chemical compounds, highways, maps, airline routes, some of the other traffic for the internet. In fact, one of the very critical thing is being discussed by White House is the net neutrality concept. And anybody knows what is net neutrality? Have you heard that one? Yeah. Would you share it with us?
Pretty much, like everything is going to be bundled, as in, like there are certain packages that you need to buy within your internet provider. Like you have a certain like entertainment for YouTube, Facebook, like Snapchat, and maybe I think it's December 14th is when they vote on whether or not to pass.
Right.
Or
right. So the Obama administration versus the new administration, they actually have different views on this one. So the new administration, they say, we'll give this power to the ISPs, internet service providers. They will decide what traffic speed they can assign based on their vendors, based on their service providers. For example, if Netflix is willing to give much higher, willing to pay much higher price to the ISP, they will have the higher speed available for the consumers to access Netflix. If Netflix says, oh, we are not going to provide you higher service charges, or the consumers are not willing to provide higher fee for accessing Netflix content, they will have the slower speed. So in other words, the deciding factor will be internet service providers, how much speed they want to provide to each one of those websites. So it's a different discussion, but graph theory can be applied in that case as well, especially if you access certain websites midnight, it will be much faster. If you access the same website around 5 p.m., it will be slower because of the traffic. A lot of people are trying to access the same website or same route at that time. So analysis of electrical circuits, finding the shortest route, project planning, linguistics, genetics, social science, and so on and so forth. In fact, I was listening to one of the TED Talks a couple of days ago that one scientist, his entire genome, DNA sequencing was done. And just for one individual, the sequences is equal to more than 250,000 pages. So 250,000 pages of sequencing of these characters. You know, A, C, T, G, these are the characters of the DNA. So just one individual sequencing is worth about 150 kilogram weight for the paper they carry. So 250,000 pages. Each page is filled with these sequenced characters. So if you want to figure it out, and they are trying to figure it out, what if we apply machine learning? If machine can figure it out, what kind of problem this person can have because of the genetic sequencing? Is he or she can have these diseases, or they can potentially have these diseases. In fact, they took the real person's face, the picture of the real person's face, and from the machine learning sequencing of the facial genetic information, they allowed machine to draw the picture of the person, and it was very much similar. So the picture drawn by a machine learning, by looking at the sequence of those characters, and the real picture of that person was identical, which is shocking that in the future, by applying the graph theory, they can actually figure it out if one of the characters is missing from the sequencing of that person's DNA, that can have certain potentially can have diseases, or those diseases can be they can find cures for those diseases. In fact, that's how it's going to happen. The future pharmaceutical industry is going to customize medication for individuals. So it will be applied based on the sequencing of your genetic information. So these are some of the areas you can think of where this can be applied. So here's an example of a graph, assuming these are the airlines. So let's say an airline based on Atlanta starts from point A, or we call it vertex. This is the starting point, 1. And it flies to point 2, or vertex 2, then from 2 to 5. And these could be specific locations. These could be Denver, these could be Memphis, Tennessee, or specific locations. Now, notice that from point A, or vertex A, it goes to multiple locations. Now, in this case, by looking at this graph, it's called indirected graph, because it doesn't tell me in which direction the data is flowing, or information is flowing, or the flight is actually flying. So it doesn't tell me it's going from point 1 to point 7, or vertex 1 to 7, or 7 to 1. It doesn't tell me. So that's an example of indirected graph. So again, there's another example here. In this case, from point 1 to 2, 2 to 4, and nothing happens after 4. So there is probably null pointer after 4. So if you want to put this as a linked list, this will be a null pointer after 4. From 1, again, you can go to 3. From 3, you can go to 5. From 3, you can also go to 6. And from 6 to 7. Now, by putting these specific locations, assuming it's a flight information, from San Francisco, you can go to LA. From San Francisco, you can also go to New York. From LA, you can go to Dallas. Notice that there's no direct flight from San Francisco to Dallas in this case. So you have to go through New York to Dallas or from LA to Dallas. From New York, you can go to London, you can go to Paris, and you can see other options as well. So this is another example of indirected graph. It doesn't tell me what direction we are going, but it's just telling me the points are connected in that case. So these vertices. And this is called an edge, as I indicated earlier. So these are the edges. And we can assign weights, which we'll do that later on in this chapter. And the weight could be based on the cost for flying from San Francisco to London. It could be a cost. Let's say it's $1,000, for example, or $700. And let's say if I go from San Francisco to New York, let's say this is, just throw a number, 300. And there is a special deal available from New York to London. Let's say that's $300. So again, if I can get your attention, from San Francisco to New York is 300. From New York to London is another 300. Special deal is going on. So what's the total cost? 600. So 300 plus 300, 600. Let's say the direct flight from San Francisco to London is 750. So now if you apply the graph theory, this will be more efficient as far as money is concerned for the consumers. Consumers can save money if they actually go through New York to London. So in fact, this is 4 or 5 years ago. This has nothing to do with our chapter, but just want to show you, people actually think about these things. There was a young person. He actually started thinking about it that if I want to go to, let's say, Chicago from Los Angeles, the price of the ticket is $450. Let's say within 2 weeks time frame. But if I go from another airport, let's say Denver, and then I want to go to Chicago, it might be different. So he actually developed a website. And anybody knows the name of the website? He developed a website called Skip Lagged. And I'm not sure he applied this theory or not, but that's a concept which has saved a lot of money to a lot of people. Many of the large airlines, they took this individual to the court. They said, you are exposing our secret, our trade secret. All the airlines, they have trade secrets. So in certain airports, the price of their travel is very inexpensive. So for example, let's say from LAX to New York, there's a special deal. Let's say that ticket is $300. But LAX to Chicago directly is much higher because of the higher traffic. So he was able to figure it out that if I actually can find a flight from LAX to New York, which stops in Chicago for, let's say, an hour, 2 hours, I can actually exit the plane and I can save $150 to $200. So that's where he created this skip lagged website. So if I put from LAX to, let's say, Chicago, let's say O'Hare Airport, this one here, let's say whatever air time is, and let's make this one-way ticket. And if I search on this one, so it's searching for LAX to O'Hare, it's showing me there's a trick to this one. And in fact, I can go for 11 p.m. tonight, reach 5 a.m. It's only $81. Because this airline is actually going somewhere else. So it's actually giving you an option that don't take a checked-in bag, just take a carry-on and exit the Chicago airport for only $81. Now if I check the same airline, and this is actually on United website or United airline flight, and if I go to United flight, and if I check the same flight from LAX to Chicago, And for the same date, December 11th, for example, and one way. So let's see what the price they show us. Remember, the price from the skip lag was $81. Here it is showing me the minimum price is $170. So you save almost more than half. So this is very significant. And this person probably must have applied graph theory in this case. So it really can be applied and implemented to save a lot of money. So just to give you an idea, and this is one of the secrets. And in fact, they took him to the court and they said, why you're exposing our secret to other people? Because if I want to go directly to point A, especially sometimes, let's say you have an emergency, you have family emergency, you have to go to a certain airport, Denver, for example, Colorado. So the price might be $800 because you have to fly next day. But if you take a flight somewhere else, which is not very popular, or which doesn't have a lot of traffic, let's say you somewhere in Ohio, Cleveland, Ohio, assuming. So, but it has a stopover in Colorado, Denver, Colorado. You actually take the flight for Ohio, Cleveland, Ohio, and exit at the Colorado. They're recording me, and they probably will sue me. But this is I have done it, and I can tell you, you can save 50 to 60%, sometimes 80% the price of the ticket. Especially at the last moment, you can save significant amount of money. And this is also applicable for international flights. The only time it doesn't work very well if that's the last airport. Let's say airport such as Vancouver Airport. There's no other airport. Unless there's a smaller airport, it goes to some other place. So, but if the airport is in the middle, you tend to save a lot of money. If the country is in the middle somewhere, let's say you are planning to go to Asia and there's a stopover in Europe. And you can actually get a ticket for Paris probably for $400 or less because the ticket for the Asian area is much cheaper. Just to give you an idea. So the graph theory has real applications in this case. Okay, so these are the directed graphs. So, and we'll discuss various directed graphs. So various directed graphs. Here's a graph 1, here's a graph 2. So here is our vertex 1. So from vertex 1, it has 2 destinations or 2 edges. You can go to vertex 2 or vertex 4. From vertex 4, you can go to 2, you can go to 3, you can go to 5, and so on and so forth. And here's another example of another graph. And I'll show you how the data is presented. How the data is presented. I'll show you once we get to that point, how you actually save the data and how you're going to save the data for your example as well. So in fact, this is a similar graph, 0 to 1, 1 to 2, 0 to 3, 6, and so on and so forth. Some of the graphs, they might have a vertex which is kind of standalone. It connects to one point or one vertex. So to write the programs that process and manipulate graphs, must store graphs in computer memory. So I'll show you how the data is stored and how to manipulate the data. Especially there are 2 methods to access the data and traverse the data. So it can be in matrices and it can be also in linked lists. And in our case, we'll be using in the linked list format. The same linked list which we discussed many weeks ago and we are very familiar. So here's a good example. So if I have data from graph 1 from the previous slide. So here's my point vertex 1, vertex 2, vertex 3, vertex 4, vertex 5. Let's say these are the 5 points. And vertex 1 is pointing towards 2, and 2 is pointing towards 4, and 4 has a null pointer. So these are simple nodes. Here's a simple node. 2 is a node, and 4 is a node. So data 2 is stored in a node. And all you're doing is connecting with the other nodes. We have done this one. And here's vertex 2 points towards 3 and 5. And 3 itself has nothing to point to, so it's pointing towards null. And point 4 points to 2, 3, and 5. Okay. And here's another example where you have the second image we had in the previous screen. So these are also available in your book. So if you look at image or figure 20-4. Okay. I don't need to explain, but it's kind of similar to that one. So this image can be converted into graphical view, which is this one here. So this image is of that type, graph 2. So again, when you're reading this chapter, it will be a little bit more clearer. So that image can be stored in the computer memory like this. So this is how data can be stored. If the data is stored in a linked list format, then I'll show you how we can actually traverse through this graph. And the traversal itself is not very difficult. Some of the things which we'll be using are existing class and unordered linked list. Those things will be in place already. I'll show you just how what method you use to access from first vertex to the second node and third node and so on and so forth. Okay, so the operations are very similar, like we did discuss these operations in the past as well. So some of the common things we apply, how to create a graph. That's the first thing I'm going to show you in the demo file as well. In fact, that's the only critical thing. And the second thing, how to traverse the graph. So create a graph, traverse the graph. So other things, checking if it's empty, checking if it's full, checking if how to print it. That's simple stuff. And remember, our goal would be to, once we access one vertex, never to revisit that vertex again. So if I have displayed a vertex, let's say the data in that vertex has been displayed, I don't want to revisit that one. So that's the only thing different in graphs. Once you have visited it, so there should be some kind of pointer, we'll call it visited. That's exactly what we'll be using. So that pointer tells me if I already have visited this particular node or this particular vertex, so I don't need to redisplay that vertex. So check the graph is clear, create the graph, and those kind of things. Few other operations might be, we'll look into a few other operations as well, but for linked lists, for each vertices, they are right next to or adjacent to each other, are stored in a memory. We looked at it earlier. In a directed graph, vertices adjacent to V are called immediate successors. So if you have V immediate to V, let's look at the graph itself. So this is our vertex here. So this will be our immediate successor. So immediate successor might be pointing towards. So this is just a term, and in our case, for our demo file as well as for your homework, you'll be using unordered linked list. You can use the ordered linked list as well, but that's what the chapter discusses in this case. Right. So again, for abstract data type for ADT, so this is will be given to you, so you'll have the access to these things. But our goal is to make sure we create, clear, print, traverse, and check the size of the graph. How many vertices are there? I'm going to add one more thing to it for your homework. I also would like you to calculate the weight for each one of the edge. So if for example, if I give you two vertices, say vertex 1, 0, and 1, these are the two vertices. So if I give a weight here, let's say 12, and if I give you another vertex here, let's say the weight is 13, and here is another vertex, let's say weight is 5, assuming these could be miles, these could be dollar values, these could be anything. So what if I ask you to calculate the weight between vertex 0 and 2, either directly this way or maybe indirectly this way? So you should be able to, when you're traversing it, you should be able to have a variable which calculates the total weight assigned to those edges. So this is one edge, this is another edge, this is another edge. So that will be added to our assignment as well. Okay. So traversing a graph is similar to traversing a binary tree. A graph might have cycles, might not be able to traverse the entire graph from a single vertex, which is possible because there might be some vertices. They are not connected directly to this here. So let's say 6 is sitting here. So this vertex, I cannot start from 0 and get to 6. It's not possible. You see what I'm saying? Because if it's a directed graph, I can only access from 0 to 2 or 0 to 1 or 2 to 1, but I cannot go from 1 to 6 or 0 to 6. There's no direct link between them. So this node 6, or this particular vertex, I have to access not through in the same cycle. So that's what it's saying. The entire graph from a single vertex might not be possible, especially when you're trying to traverse it, print it, and so on and so forth. So these are the two methods or algorithms, depth first and breadth first. These are the two ways you can actually traverse and either modify the data or display the data. So my demo file will have the depth first, which is right here. In depth first, so mark node V as visited. So once you actually have visited a node, let's say you start from this point, so you mark as visited, which means I don't need to come back to this particular one again. And for each vertex U adjacent to V, let's assume this is U, this is V. So when you go from here to here, if U is not visited, start the depth first traversal at U. So figure it out if you have additional vertices here. So if this is V, this is U. So if you have visited V, mark that one as visited by your pointer. There'll be some kind of variable. And then you go to U vertex. Once you have visited that one, if you have not visited that one, figure it out if there's additional vertices underneath. So you want to visit those as well. So that's what it's saying. Start the depth first traversal at U. And it looks like it's a recursive function. Until and unless you find the null pointer, continue to flow in that direction. Okay, so here's a good example. So in this example, so you have this is your depth first. So I really want you to pay attention for this one, because this will really allow you to understand the differences between depth first and breadth first. So in case of depth first, if you are traversing this graph, assuming this is what the graph looks like, and so from zero in depth first, from 0 you will go to 1, as you can see, from 0 to 1. From 1 you have this a link here, so you'll go to 4, so 0, 1, 4, and then 4 doesn't point to anything. So 0, 1, 4, that makes sense, but 4 is not pointing anywhere. So of course we cannot go anywhere else. So every time you visit these 3, you want to mark them visited, 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 so those cannot be revisited the second time. Then you go to, in this case, in depth first, you go back here, you go start from 3, from 3 you go to 2, from 2 to 5, from 5 to 8. So that's exactly you see 3 to 2, 2 to 5, 5 to 7. Sorry, 5 to 7, because it has 2 different ways or links. So from 7, there's nothing else to visit. Then you go to 8, that's immediately after 5. You go to 8, and there's nothing else to visit. Then you go to 6, there's nothing else to visit. Then you go to 9. So that's your depth first. Okay. Now this is a simple example, and the good news is for our homework assignment, it will be a simple example as well. But these could be the airports. These could be the circuitry. This could be the internet traffic. It could be anything. So you can apply these concepts to any one of those things, and you can assign weights to each one of those edges. Now, if I can get your attention again for the breadth first, notice that from 0 it goes to 1, from 0 to 1, and then it goes back to 3, because this is your starting vertex. This is the first one, so it goes to the first successor. Then after that it goes to the second successor, which is 3, because it's breadth first. So it's from 0 to 1, then 3 to 4. 3 to 4. So it's actually accessing the breadth of the graph first. So it's not going to the depth, it's going to the breadth. So 0 to 1 right here, then 3, then 4, then 4 to 2, and then 2 to 5, then 7. 7 actually is not pointing anywhere, so 7, then 8, then 6, then 9. So that's a different way to access or traverse the data. So it's different from, so in this case, the breadth is covered first, not the depth. So that's a slight difference between those two algorithms. So in breadth first of a graph, similar to traversing binary tree, level by level. So it's by level by level. The other one is by depth. So nodes at each level are visited from left to right. So if I go back here, nodes are visited from left to right. So after this was visited, then left, then right, then it went back here. I think it went to 3 to 4, then 2 to 5. So left to right, level by level. So seems like this actually has a higher level, then this level, then this level. So that's your breadth first traversal. Nodes each level are from left to right, and starting at the first vertex, the graph is traversed as much as possible. Then go to the next vertex, not yet visited. Use a queue to implement the breadth first search algorithm if you need to search in the breadth first algorithm. Again, I did mention that weight is a non-negative real number. Weight could be dollar value. Weight could be miles, as I indicated with various examples earlier on. Weight could be the time period. It could be hours. In fact, for the flight information, if you are trying to figure it out which will take you to a location from location A to location B faster, then it could be the time frame. Every edge has a non-negative weight assigned to it. And this can be assigned by the airline industry or by the internet service providers or by the trucking company. So they can assign certain values. They can say, okay, from this point to this point, this is how much it costs us. This is how much gasoline we spend or energy spend, or this is how quickly we can actually reach our goal, like let's say a sales goal, for example. So sum of the weight of all edges on the path P, so you can add all the sums and also call the weight of V, vertex V from U, which is the immediate successor of V, via P. So starting vertex in the path. So you start from the top, from the first vertex, and continue to add the weights to get the sum of all the weights. Now shortest path will be, and we'll see a couple of examples in the shortest path, especially you're trying to reach earlier to point B or a certain vertex. So that will be your shortest path with the smallest weight. Shortest path algorithm called the greedy algorithm. Again, that's just the name, greedy algorithm. And you will see that how we can actually get to that particular location, and it gives you the pseudocode, and I have the example which I'll demonstrate that to you. So here's an example. So if you can take a look at this particular graph. So we have vertex 0, and then we have other vertices with it. Okay, so let's analyze this one. And there are 5 or 6 slides based on this particular graph. So each one of these edges, they have a weight assigned to them. Just by looking at it, I can tell, let's say this is LAX, and let's assume this is Denver. That's a Denver airport. So although they are not too far off, they are not that distance-wise, they are not that far, but it's very expensive to travel from 0 to 1. The weight is 16, assuming there's some kind of large convention happening. So, and it happens in the hotel industry. So if there's a large convention, the prices of these hotels go higher. So assuming this is way more expensive, then as a smart consumer who understands these graphs, or graph theory, he or she can apply graph theory in this case. So I can actually go to, let's take a look here, from 0 to 3 and 3 to 1. So this will be 2 plus 12, 14. I save money. I save a couple of dollars, or $200 in this case, because this weight is 2 plus 12 is 14 versus this is 16. Or I can go from 0 to 4 and 4 to 1. And in this case, I save $300. 10 plus 3 is 13. You guys are following? Or is there any other way I can find cheaper way? And actually, it shows you in the next couple of slides. So here, from 0 to 1, the weight is 16. From 0 to 3, weight is 2. 0 to 4, weight is 3. As you can see, the weight is 3. And from 4 to 2, weight is, there is no direct, there is, so 4, 3, 7. I'm not sure what this indicates. I'll probably come back and visit it. Let me take a look here. 0 to 4, 4 to 0 to 4, 4 to 2. Looks like there is a direct connection, but I'll come back and visit it. So these are the weights assigned to each one of those vertices and edges. So graph after first iteration of steps 3, 4, and 5. After 3, 4, and 5. So here, if you are from 0 to 1, 16. So if you go to, let's take a look. Help me out, guys. What's happening here? 3, 4, and 5. 3, 3, 4, and graph after the first iteration of steps 3, 4, and 5. Okay, so it looks like this is 0 to, this is 0 vertex, 1, 2, 3, and 4. So between those two is 14. So it's looking at basically 0 to 3 and 3 to 1. That's actually 14. 3 to 1. Yeah, that's 14. So that's what's indicating here. And I have already demonstrated this one. So here you can see 0 to 3 or 0 to 4 and yeah, so that's 3, then 4 to 1, that's 13 right there, 13. I know the way it's indicated here, it's not that very clearly visible, but what we are trying to understand, how we actually can find the lowest possible weight. So if you look at this one here, 0 to 4 and 4 to 2. So this actually is 3 plus 4 is 7. And if you take from 2 to 1, 7 plus 3 is 10. So in this case, the weight is 10. So again, 0 to 4, 4 to 2, 2 to 1. If you add all these weights, 3 plus 4, which is 7, 7 plus 3 is 10. So this will probably be the cheapest way to, or the most efficient way to get there from that point to other point. Okay, so I indicated that one. So company needs to shut down a maximum number of connections and still be able to fly from one city to another city. Okay, so that's another problem. So this problem can be solved by the graph theory. Now, what do you think? Do you think the decision makers, they are really applying these graph theories when they are looking at their flight schedule? Do you think they have some people analyzing this kind of data in a graphical way and applying these theories and from that perspective? I believe so. It's possible because it's a very quick way to make those decisions. You can actually still run numbers and do some kind of use a grid method and use some kind of other methods. But this is a quick way to graphically look at the data. So assuming These are the different types of connections they have. And they are trying to cut down some of the connections and still maximize the profits. Company needs to shut down a maximum number of connections, still be able to fly from one location to another location. So then they can apply these kind of three different graph methods. So if you look at this one, so they can still fly to all the major locations for that airline. Graph A, graph B, and graph C. Then by looking at it, it might be expensive for the company to fly from 4 to 5, which is the weight is 10. But if you look at this one here, if I use this one, if I go from 0 to 2 and 5, that weight will be 12. In this case, weight was 10. If I look at this one, from 0 to 2 and 2 to 5, weight is 12. So the weight is 12 from 0 to 5 in this case, weight is 10, and weight is 12. So if I want to go to location 5 or vertex 5, the middle graph might be a little bit more practical or more beneficial. So that's how they can evaluate each one of those locations. And these weights could be, like I stated, cost per seat, how much it costs them per seat. Do you know how much money do they make for each seat on a typical commercial flight? Is it possible if you are flying on a seat, the person right next to you might be paying double or triple the cost you paid, the price you paid? It's possible. It is possible that, let's say you got the same ticket for $80, somebody else paid $800, 10 times? Absolutely. Absolutely possible. And so your goal as a consumer, apply these graph theories and see if you can benefit from these theories as well. All right, so simple graph such that if U and V are two vertices in graph T, then there is a unique path from U to V. So that's a tree or free tree. There are 2 or 3 types of trees are discussed here. Rooted tree in which a particular vertex is designated as a root. So remember, when we discussed the binary tree, there was a starting point. So here, rooted tree actually has the same concept that one vertex is the starting point. It's the hub. That's what we call it. So some airlines, their hub is Dallas, for example. So that will be their rooted tree. So everything actually, in fact, if you have seen some of their airline magazines, at the last couple of pages, they show their entire graph. Of course, they don't show you the edges and the weight of edges. They show you the edges, but not the weight of edges, that how much it costs them to fly from point A to point B. But you can actually see that they have the graphical view already in place. Or you can go to their website and you can see, just type where exactly this so-and-so airline flies, and it will show you that particular graph. So weighted tree in which a weight is assigned to each edge. That's the weighted tree, which we have been discussing for some time. So weight of T, weight of the entire tree, sum of the weights of all the edges. So that will be the weight of T. Or it's the cost for that airline or that service provider to conduct business in the entire organization. That will be the weight of the entire tree. And it is denoted by WT as shown in the slide. So 2 well-known algorithms to find the minimal spanning tree. So there are 2 algorithms. Some of these mathematicians, they have developed those algorithms. So you can actually build the tree iteratively by adding edges until a minimal spanning tree is obtained, which means minimum weight is obtained. Start with a designated vertex, call the source vertex, start from one point, and each iteration, a new edge that does not complete a cycle is added to the tree. So you can start from one side and continue to access the other vertices so you can start from 0 and then continue to visit other vertices. and find the weight for this tree. Then Prim's algorithm is shown here. Let's spend a couple of minutes on this one. So here, and you can see these are the points shown here from 0 to 1, the weight is 6. As you can see, 0 to 1, weight is 6. 0 to 2, weight is 5. 0 to 2, weight is 5. 0 to 3, weight is 2. So 0 to 2, 0 to 3, weight is 2. So this is the least, weight in this particular, in these roots. And then you can add them together. You can add them together to figure it out what is the total weight. So here in this tree here, 0 to 1 weight is 6, 2 to 5, which is right there, weight is 7, and so on and so forth. So this is in this tree, the weight, the minimum weight is 5. In this case, from 6 to 1, weight is 4. And in this case, 0 to 2, weight is 5. So you can find the minimum edges in this case. And continue with that from the previous one. So from 1 to 4, weight is 2. That's the least or I should say minimal. And then 2 to 5 is 7. That's the least. Then you add up all the numbers, all those sets you made in the previous 4 or 5 images, 0 to 3, 0 to 2, 2 to 6. So each one of these are minimal weights. If you add them together, so edges of the tree, they're added together as sets. When you add them together, you find the minimal spanning tree. So this is one of the theory they use. This is the algorithm that they use to figure it out, the most efficient or the total weight of that tree in a most efficient or minimal possible way. Okay, so those are some of the concepts we use in this chapter. So what I'm going to demonstrate now, I'm going to show you how we can actually create these trees in this case. So if I can show you my main function first. In my main function, I actually have, I'm calling 2 methods. One is create graph. And notice that this graph has I'm planning to have 50 elements or 50 nodes and 50 data types or data points. And I'll show you what data I'm going to use. You can use any data you like. But if you remember the unordered linked list, there should be some kind of ending point when you're reading the data. I'm not going to read the data from the user. It's just waste time. I'm going to read the data from our file. I'll show you my file in a minute. Then once the graph has been created, I just want to look at it. I want to do the traversal, depth first traversal. So my main focus will be in those 2 functions. But there are a couple of additional functions which will be called from a create function and depth first traversal function. I'll discuss those as well. The other methods and the abstract data types, they're already given to us. So they are already from our previous discussions. So I'm going to just revisit them for a couple of minutes. Here's my node type. Node type, just for the lecture, for the recording. Here's my struct node type, info, and link. This is what we did in chapter 16, if you remember. So we are very familiar. It's just a node. So I can actually store the data, and I can have a link to connect with the next node. And then I have my linked list iterator. This will allow me to figure it out that how do I access from one node to the next node to the next node and so on and so forth. We have discussed this one in the past. This only allows you to cycle through your iteration, cycle through your linked list. And this is your linked list. Nothing is new in this linked list. It only, let me just show you a couple of things here. It only allows you to figure it out if the linked list is initialized. If it's not initialized, destroy it. If it's empty, check if it's empty. Same thing we discussed in the few examples in the past. If it's empty, tell me if it's empty. If it finds the null pointer to the first pointer, if it's empty, let me know. If you want to print it and you have a current pointer which goes to the first head or root and cycles through. Again, this is not new whatsoever. This is just allowing you to see what we did in the past. So display the information, go to the next link, and it cycles through this one until you reach the null pointer. So this is something we have done in the past, but we are just using this one for our abstract data type implementation. So same thing, checks the length, returns the length, destroys it, checks the first, again for the camera. So it checks the length, checks the first, the front of the linked list, checks the back of the linked list. If you need to search, in this example, we are not going to search, and you're not required to search as well. But if you want to search, it's already embedded there. You can simply apply it. So notice that these are virtual methods. In fact, these are pure virtual methods. As you can see, equals to 0. So these must be implemented at the lower end, which we already have implemented in the past. So I'm going to skip all this stuff. I'm going to minimize this one. So, and then our unordered linked list, which we also developed, is a derived class based on linked list class. All this class is doing is inserting a node. Maybe if you need to search, it has the ability to search. Again, you're not required to search for assignment number 7. Check if the unordered linked list is empty, how many nodes are there. All those basic functionalities are available. So just to show you, just to insert first. And this is the same thing. When the data comes in, and we have discussed in the past, the data comes in and assign the data to info and go to the next link. Insert last, delete node, and that's it. So that should not be a problem. So then we create a class. That's the class I want to focus on. We create a class called graph type. So that's a class, and that's the object of that type I created in my main function, graph type. So that's where you want to pay attention as well for assignment 7 and for this demo. So notice that I have maximum size and Gsize. And I'll talk both of these once we start implementing. But just for your understanding, maximum number of vertices and current number of vertices, which means, let's say at the time of the creation of my graph, I say 50 vertices or 50 nodes. So that will be a maximum possible size. But at the time of the creation of your graph, you add only 10 vertices. You only add 10 data points. So Gsize will be only those 10 points, although the maximum size might be 50. Let me highlight this one further. Let's say this is my data point. So in this case, I'm only interested in adding 10 vertices. 10 vertices. From 0 to 1 to 3, from 1 to 4, 2 to 5, 3 to 2, 4, 5, 6, 7, 8, 9. So there are 10 vertices here. 10. From there, we can add additional data. And these are the ending points. This is just in my code. When I'm picking up the data, when I find minus 999, it means that's the end of data for that particular for that tree, for the graph. So then again, we check if it's empty. We can check if the Gsize. Remember, Gsize is the number of vertices we have added. If it's 0, it means there are no vertices. There's nothing to read. So the graph is empty. Then I'm going to spend time on create graph. That's where I'm going to focus on. I'll come back to that one in a second, but I just want to show you a couple of other things. So this is clear graph. So clear graph is basically goes to each one of those nodes or vertices and clears them. As you can see, clears them or deletes them and makes your Gsize equals to 0. Just in case, if you want to create a brand new graph, you want to clear the previous graph. And the print itself is really simple. Print itself says, I'm going to run through this index less than Gsize. Again, Gsize could be 10 vertices you added or 20 vertices you added. So it's going to cycle through 10 or 20 times based on the number of vertices. And it says, okay, show me the index and print it. And then it cycles through until all of the data points have been printed. So print is just very similar to what we did in the past. Then once I actually come back to the depth first, I'll show you how the depth first reversal happens. And there are a couple of functions associated with that one. Okay, and one constructor. You can add one more constructor as well. So you can see if the graph size is provided. In my case, when I created it, I provided 50. So let me show you where I provided 50. So in my main function, as you can see, I'm interested in 50 of these nodes. So that will be the maximum size. So 50. So size is 50. So this my graph size 50 will be captured here. 50 will be captured here. So size 50 will be assigned to maximum size. And of course, if I have not assigned any specific data or created my graph yet, so my Gsize will be 0 at that time. Okay? Or at that time of the creation of the new graph, or I'm creating a new object of graph type, I'm going to make sure my Gsize graph size is 0. Then I create a new unordered linked list placeholder or a new node so I can actually add the data. And my destructor is just simply clear graph, clear graph. Okay? So now I'm going to come back and show you how the create function works, create graph function works. So I would like you to pay attention to these two functions because that's where you will be accessing these are the ones you will be focusing on for your assignment number 7 as well. So I'm going to show you the create and the depth first reversal. All right, let's look at the create one. Yeah.
Does some of this code go in like a header, different header, or is this all in the CPP?
So you can put it in the header file, absolutely. Especially you have the linked list and unordered linked list. You can throw all that one, especially when it comes to the ADTs, abstract data type, that could go to your header file, and the implementation can be in a CPP file. Here I put everything in one place, so we don't have to go back and forth. So it's easier to see that way. So I open my file, my data file, and I showed you the data file. I'm going to show you again. A couple of variables just to track, and I'm checking if my Gsize, the graph size, which I am planning to create, if it's not equal to 0, clear graph, which means clear all the previous, if there's a graph, clear it. And just checking the file, if file exists, doesn't exist. And then let's keep this one here. Then it reads the graph size. Remember, there's a slight difference between maximum size and graph size. Maximum size is the possibility for the entire graph. But here, in my case, I'm only intending for 10 of these vertices. So I pick up that value, number of vertices, right there. So I'm picking up that value right there. And then it will display this value, size 10, right there. Just to verify that that will be the number of vertices. Then once I actually know there are 10 vertices, so 0 through 9, there are 10 vertices, then I want to pick up each vertex or successor. Each vertex or successor. So I pick up 0 here, I pick up 0 here, and I also pick up the adjacent vertex or successor. So immediately after 0, I have 1, so I pick up that information as well. Then I display it. Then I say continue to pick up all these values until you find minus 999. So it goes here, picks up 0, picks up 1, picks up 3. At one stage, it becomes minus 999. So when it finds minus 999, it will stop right there. And that's what we are checking here. Let me put this one here. Right there. And while we are picking up each one of these vertices, we are calling the insert function to insert that particular adjacent vertex next to it. And continue to pick up the next value. And if it's not in minus 999, display it. And this stays in this loop until it finds minus 999. So in this case, for the first vertex, the adjacent vertex, which is right there, is 1 and then 3. At one stage, when it finds minus 99, it stops. Then, once that's done, it goes back to the outer loop, and it knows there's 10 of these. Then it works on the next vertex, which is, so we just processed the first few vertices. Then it goes and picks up this one, and then goes through the same loop and finds minus 99. In other words, it will create the entire graph, and it would look like this. When I run this one, it will look like this. I made it a little bit more presentable. In the book, it's not like that. I just wanted to make it very clear to you. So you pick up the size, number of vertices here. That's the Gsize. That's the Gsize I have in my data file. And that's, you can see, 0 to 9. Those are the number of vertices. And each adjacent vertex, for 0 vertex, 1 and 3. For 1, 4. For 2, 5. And if you look at the data file, let me put the data file right next to it. It will make more sense. So there are 10 vertices. So you create the Gsize for 0, 1, 3. For 1, 4. For 2, 5. Notice that for 4, there are no adjacent vertices. So that's why 4 is pointing towards basically null pointer. For 3, adjacent vertexes 2. For 5, 7 and 8, as you can see right there. For 6, 4 and 7. 7 has no adjacent vertex. 8 has no adjacent vertex. And for 9, 7 and 8. And this is the depth traversal. And I'll show you the traversal in a minute. This is what we discussed earlier. So it's going to go to 0 and 4. And especially it's more visible and it's more understandable when we see the graph itself. It's going to go to 0, then 4, then 3, then on and on. Because 0, 1, and if you have the imagery available from 0 to 1, and 1 is connected to 4, so it's going to go to the depth first. So let me talk about the depth first traversal. Let's see how it works. I think I'll bring this one again. So we have a pointer variable called visited. As you can see, visited. And we are assigning the number of vertices here, or creating the number of variables of that type, assuming it's an array of size 10, because the Gsize is 10. So literally, we have 10 of these visited holding areas. So we can assign either true or false. If I already have visited this one, it means I need to indicate that I have already visited that one, and I'll show you how that is indicated. So initially, all the 10 of these visited pointer variables, their values are false. So I just ran a very quick for loop, and all of them are assigned false value. Now if I visit one of the vertices, I want to change into true. All right, how do we do that? So that's the trick here. So let's look at this loop here. And that's the heart of this traversal in depth first traversal, that I go through this loop from 0 through 10, Gsize is 10, and I check if not visited, zeroth index. So we have 0, index is 0, zeroth index. If it's not visited, so call this DFT index, which you pass 0 here, and that particular pointer there. So in other words, we are trying to figure it out if I can call a function which can figure it out if I have visited that particular vertex or not. So let's look at this DFT function. And DFT stands for depth first traversal. That's all it is, depth first traversal. So this DFT is right here. So it captures the index here, captures the index and captures that visited variable, which has we have assigned 10 of those variables. So it says, okay, visited 0th index, the incoming index, equals to true because we want to check if I actually have visited this particular vertex, I want to change into true. And display the value of v, and that's how I was able to display these values. I was able to display this value here, and then go through the these are the functions given to us from the iterator. Remember we talked about iterators. They have begin function and end function, so those are already available to us. So for graph v is the 0th index. Start from the what happened? Okay, yeah. So start from the starting point, and if graph it is not equal to graph, that's one of the variables we declared, then your w equals to graph it, and then check if it's not visited, then call this function again. So in other words, go through each one of those vertices or nodes and check if they are not visited. So this is a recursive function. Every time if it's not visited, go and visit them. And it will visit each one of those until it finds the end point. So this recursive function performs the depth first traversal of the graph at a node specified by the parameter vertex. This function is used by public member functions, depth first traversal. And starting at the vertex, the vertices are printed using depth first traversal. So basically the goal is every time I visit the new vertex, if there are additional vertices available, change into true, and otherwise continue to call this traversal, recursive function. Now at one stage, there's nothing else to visit in that particular depth, and it will go back. And it's going to continue to do that until all the indices have been all the Gsize has been visited, or Gsize is 10, so started with 0, so it becomes 1, and so on and so forth. Now, our goal here is try to figure it out, because in this case, this is what we implemented. We implemented this particular method where we have depth first, 0, 1 to 4. What if I want to convert that into breadth first? Breadth first, which means level by level. Not the depth, but the level by level. So that would be our assignment for this case. So let me just highlight this one here. So our assignment itself is really simple. So in programming exercise number 1, it says write a program that outputs the nodes of a graph in a depth first traversal, which I already have given you. It's available to you. Write a program that outputs the nodes of a graph in a breadth first traversal. So the same data I'm using here, see if you can convert into breadth first. And you say, well, how do I get the logic for this one? Well, logic will be available to you. Let me see if I can go back here. here's the logic. It tells you step by step. Let me go back here. DepthFirst traversal right there. So this is on page 1417. So if you look at page 1417, it's given to you. So you need to implement it in order to process the data I'm giving it to you. Not only that, you need to also calculate the weight of edges, weight of each one of those edges. So I'm asking you to do those two things. So implement this into your code, as well as, if I go back here, So in fact, I have data file here. You can use this data file if you like. You can use any data file, but if you use this data file, I have the specific weights available. So complete exercise 2 from page 1438. And take a look at the figure 20-6 for your understanding, and calculate the weights for the following edges. So this is your data. So this is your vertex from 014, 03257, 03258, and I can draw that for you if you are not sure. I can draw in a minute. And from 0 to 1, the weight is 1. From 1 to 4, weight is 2. 0 to 3, weight is 3, and so on and so forth. So how do I draw this one? So let's actually see if we can draw this one. So here's your 0. Here's your 1. Here's your 4. So that's your first vertex to adjacent vertices. Then 0 to 3. 3 to 2, 2 to 5, 5 to 8. Okay. Then you have 0, 3 to 5, 0, 3 to 5, and 7. 5 actually goes to 7 as well. And then you can go to 6 to 4. 6 to 4. 6 to 7, and 9 to 7, and 9 to 8. So as you can see, this could be your tree. And then I have assigned weights for each one of those edges. So from 0 to 1, weight is 1. That's your weight. 1 to 4, weight is 2. 3 to 2, 3 to 2, 0 to 3 is 3, 3 to 2, it is 4, 2 to 5, it is 5, I should have used different color for that one, 5 to 7, weight is 6, 5 to 8, weight is 7, 6 to 4, weight is 8. 6 to 4, weight is 8. 6 to 7, weight is 9. 9 to 7, weight is 10. And 9 to 8, weight is 11. All right, for the camera. So here's our tree, if you want to visualize it. And these are the weights assigned to it. So your goal would be to do this. So look at the figure on page 1414 and calculate the weights for the following edges as well. So there are two steps involved in this one. One is to do the breadth first traversal, and the code is already in the book 1417. Page 1417 has the code. So implement it and then see if you can calculate the weights. And also minimal spanning tree is discussed, so you can look at this example and see if you can actually calculate the total sum weight. You can also provide me the weight between each adjacent vertices, and also, for example, if I say, how do I get from 0 to 4? What is the total weight needed? So 0 to 4, 0, 1 to 4, the weight will be 3. How do I get to 0.8, for example, from 0? So 3 plus 4 plus 5 plus 7, that will take me to that particular location. So that's how you need to calculate it. So once you read the chapter, it will provide you more information how to do that. I have theoretically discussed how to add those weights. You just need a variable, some variable which can, once you are traversing it, it's continuously adding those weights at the same time. Okay? Again, if you came late, we'll be working on assignment number 7, which will be due by this coming Sunday. And when you come back next Monday, we'll be taking our final exam based on chapters 20 and 21. That will be the last day of our class as well. For the online students, we'll be taking our exam online, but for our on-campus students, our exam will be on Monday, December 4th. All right, guys. Thank you very much.